It did. Wow. Cool. All right, so we're recording 9.2. Taylor polynomials. This section is going to be pretty quickly because it's kind of like a specific case of the next section, which is Taylor series. All right, but it is a good transition, good segue. So a Taylor polynomial is a polynomial. Of course, we know is something on the form ax to the n. We'll call it a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus ... plus maybe we'll call it a sub 0 or a sub 1 x to the first plus a sub 0, something like that. And of course, we know that what makes a polynomial is that the exponents are positive integers. Okay, or you could say they're whole numbers, either way. So if you have like a fractional exponent on your x or a negative exponent, it's not a polynomial. Polynomials are the easiest types of functions to work with. Okay, you have linear, degree 1, quadratic, degree 2. They're the easiest functions to work with, and they're the ones that kind of started off the study of all the different types of functions, which you studied in Algebra 2, pre-cal, we went to exponential, then to logs, then to the trigonometric. So what a Taylor polynomial does is it uses the relative simplicity of a polynomial to approximate other functions that are not polynomials. That would be a lot more difficult to evaluate. Because you got to remember, back in the day, they didn't have calculators. Now, we can just type in the natural log of 5, and it'll give us the decimal approximation. But how did they do that in the past? Or how do the calculators, now that we know, how do the calculators actually perform that? They perform it by way of a polynomial. So that's what a Taylor polynomial is. It's a finite number of terms that is used to approximate a non-polynomial function for different values of x. And we've been dealing with polynomials of the Taylor variety all year long because we've been writing equations of tangent lines, which brings it to this right here. Find the equation of the tangent line for f of x equals sine of x at x equals 0, and then use it to approximate sine of 0.2. Is it an over or under approximation? All right, so what do we need for the equation of a tangent line? Slope and a point. So let's find the point first. The x value is 0, and the y value is f of 0. So it's going to be 0, 0. And now I need the slope at the point, so I need f prime. F prime is equal to cosine. And so my slope is going to be f prime of 0, which is cosine of 0, which is 1. And all year long, we've been writing the equation of the tangent line. We've been calling it L of x for linearization. We've been writing it in Taylor form, Taylor form, Taylor form. Well, here it is again in Taylor form. It's the y value that we started with, 0, plus the slope, 1, times x minus the x value. And if you simplify that, in this case, you just get x. This is a first-degree Taylor polynomial centered at x equals 0. Okay, we're going to say that this is centered at x equals 0. It's the point of tangency. Now, if we figure out graphically what it is we just did, the graph of sine is Sahala. It looks like this, and it looks like that. What we just did is we wrote the equation of a tangent line that can be used to approximate, here we go, looks pretty good. It can be used to approximate the graph of sine at values of x near 0, right? Now notice 0 is the point of tangency. So the line at 0 and sine of x at 0 have the exact same y value, yes? But after that, they're different. But they are very close to each other for small values of x, yes? And so in this case, it says, what is sine of 0.2? Well, 0.2 might be right here. And if you notice, I can't even tell the difference between my line and the graph of sine of x because they're so close to each other, they appear to be on top of each other. But we do know that the tangent line is slightly what in relation to the graph of sine at this point? Which one's actually above the other? Yeah, the line y equals x is slightly above the graph of sine because the graph of sine is concave down, okay? So the idea being that in a radius, in this small little interval, we'll call it plus r and minus r. In this small little radius, this little neighborhood surrounding the center of the approximation, or the point of tangency, the idea is that x can be a good approximation for sine of x, right? So sine of 0.2 is about 0.2. And the actual sine value is a little bit smaller. Who's got a calculator? What is sine of 0.2 radians? It's going to be a little bit less than 0.2. 0.198. Hey, it's pretty good. So back in the day, if they wanted to figure out what sine of 0.2 is, rather than try and discern what sine of 0.2 actually is, they would just say, it's a little bit less than 0.2. And that would have been like, wow, okay, that's good. I like that. So that's a first-degree Taylor polynomial. It's a line. Well, if a line works great, maybe a parabola would work better. So here's what the parabola might look like. If I could fit a quadratic to fit the curve on a small window, maybe the quadratic would look like this. Okay? And so now, if I can find a quadratic equation that approximates the graph of sine in a neighborhood on either side of 0, maybe that's going to give me a better approximation. Now, quadratics aren't as easy to approximate as lines, or to plug in as, evaluate as lines, but they're still pretty easy. Well, if a quadratic is good, maybe a quartic would be better, right? Maybe there's a quartic equation that comes in here that actually is going to be a better approximation. And then by the same token, maybe a fourth-degree polynomial, so on and so forth. And there is a way then to determine what the equation of those higher-degree polynomials are. And the bigger the degree of the polynomial is, the better the approximation is. Okay? Now, I'm just going to show you here in the time that remains what I'm talking about, and then we'll get back into it tomorrow. So if I come over here and I type in sine of x, I don't know if we're going to have time. We have 3 minutes. Calm down, Mr. Corby. Okay. If I just look at x, let's zoom 6. I sure did. That's funny. That's cute. Okay. Haste makes waste. Calm down. Here we go. All right, there's sine, and here's the graph of x. So again, you could see if I go too far to the left, the line is no longer a good approximation. But what if I step it up and I come up with a quadratic? Maybe a quadratic equation, maybe there is no quadratic. There's actually not. So the next one, as you're going to learn, is to be a cubic. But in theory, we could step up degrees, and I'll show you how we're going to generate these terms. If I do that, there's a cubic polynomial. Look what happens with the cubic. Oh, did you see that? It kind of comes in over here, and it starts wrapping itself around the graph of sine of x. And so maybe I can use the cubic now as an approximation. Well, if the cubic is good, maybe there's a fourth degree polynomial. Well, actually there isn't, but maybe there's a fifth degree, and there is. And I'll type it in here, x to the 5 divided by, it's going to end up being 5 factorial, which we can get by going math probability 4. So if I hit graph, look what this looks like. By the way, I'll show you how to generate these terms. So notice the fifth degree polynomial comes in a little bit farther to the left, kind of simulates the graph of sine of x for a longer interval, and then departs. So we're still centering it at the origin, but now I can drift a little bit further left and right from 0 and still come up with a pretty decent approximation for sine by just evaluating a polynomial. Well, there's going to be one that's x to the 7th, and x to the 9th, and x to the 11th. And the more terms you include, the more it's going to wrap around the graph of sine of x. And that's what the idea of a Taylor polynomial is. It's a polynomial that will wrap itself around some other non-polynomial function. Okay? Have a fantastic day. We'll see you back tomorrow.